Add up 1 plus 1 fourth plus 1 ninth plus 1 16th plus 1 25th and keep going forever. Every term is the reciprocal of a perfect square. The sum converges, it has to, because the terms shrink fast enough. But here is what nobody expected. The answer involves pi, not approximately, exactly. Pi squared, divided by 6. There are no circles anywhere in this problem. No arcs, no radii, no geometry at all. Just whole numbers, squared and flipped. And somehow, pi is hiding inside them. Let's build the sum term by term and watch what happens. The first term is 1. Add 1 fourth and you get 1.25. Add 1 ninth and the sum climbs to about 1.361. After 10 terms, it reaches 1.549. After 100 terms, 1.635. After 1,000, 1.644. The sum is creeping upward, but slower and slower, approaching a number just above 1.64. And that number turns out to be pi squared over 6, which is approximately 1.64493. This was one of the great open problems of the 17th and 18th centuries. It was first posed in 1644, and for 90 years the best mathematicians in Europe could not find the exact value. Pietro Mengoli asked the question. Jacob Bernoulli tried to solve it and failed. His brother Johann also tried and failed. The problem became famous precisely because it resisted everyone who attempted it. Then in 1735, Leonhard Euler, just 28 years old, cracked it using an argument so bold that even he could not fully justify it at the time. To understand what Euler did, we need to start with something familiar, the Taylor series for the sine function. Every calculus student learns that you can write sine of x as an infinite sum of odd powers of x. The first term is x itself. Then you subtract x cubed divided by 3 factorial. Then add x to the 5th over 5 factorial. Then subtract x to the 7th over 7 factorial. This pattern continues forever, alternating in sign with the denominators growing as factorials. This series is not an approximation, it is exact. For any real number x, if you add up infinitely many terms of this series, you get exactly sine of x. The series converges everywhere. It represents the sine function completely. That is a remarkable fact. It means that sine, this smooth oscillating wave, is secretly an infinite polynomial. And Euler realized that if sine is an infinite polynomial, maybe we can treat it like one. The first step is to divide both sides of the Taylor series by x. On the left, we get sine of x divided by x, which is the sinc function. On the right, we get 1 minus x squared over 6 plus x to the 4th over 120, and so on. Notice that the right side is a power series with only even powers of x. It starts at 1 and decreases. The key term is the x squared coefficient. That coefficient is negative 1 over 6. Write that down. We will need it. Now comes the crucial question. What is the x squared coefficient telling us? In an ordinary polynomial, the coefficients are determined by the roots. If you know where a polynomial crosses 0, you can reconstruct its coefficients. For example, if a quadratic has roots at r and s, then the coefficient of x in the expanded form is negative r plus s, and the constant term is r times s. The roots determine everything. Euler asked a dangerous question. What if we apply this same logic to sine of x over x? It is not a polynomial, it is an infinite series, but it behaves like one. It has a value at every point. It crosses 0 at specific predictable locations, and those locations are well known. Sine of x equals 0 whenever x is a multiple of pi. That means sine of x over x equals 0 at x equals pi. Negative pi, 2 pi, negative 2 pi, 3 pi, negative 3 pi, and so on. Every non-zero integer multiple of pi is a root. If we pretend that sine of x over x is a polynomial and factor it using its roots, we would write it as the product of terms like 1 minus x over pi, times 1 plus x over pi, times 1 minus x over 2 pi, times 1 plus x over 2 pi, and so on. Each pair of roots, the positive and negative version, contributes a pair of linear factors. But here is a nice simplification. Each pair of linear factors multiplies together to give a single quadratic factor. 1 minus x over n pi times 1 plus x over n pi equals 1 minus x squared over n squared pi squared. This is just the difference of squares formula. So the entire infinite product simplifies to the product for n from 1 to infinity of the quantity 1 minus x squared over n squared pi squared. Now we have two different expressions for the same function. The Taylor series gives us sine of x over x as 1 minus x squared over 6 plus higher powers. The infinite product gives us sine of x over x as the product of 1 minus x squared over n squared, pi squared for all n. Both expressions are equal, they represent the same function, and that means their coefficients must match. Let's extract the x squared coefficient from the infinite product. When you expand a product of the form 1 minus a 1 times 1 minus a 2 times 1 minus a 3, the coefficient of the first order term is negative a 1 plus a 2 plus a 3 plus all the rest. In our case, each a sub n is x squared over n squared pi squared, so the x squared coefficient of the product is negative. The sum of 1 over n squared pi squared, for n from 1 to infinity, factor out the 1 over pi squared, and you get negative 1 over pi squared times the sum of 1 over n squared. Now the magic happens. We have two expressions for the x squared coefficient of sine of x over x. From the Taylor series, the coefficient is negative 1/6. From the infinite product, the coefficient is negative 1 over pi squared times the sum of 1 over n squared. Since both expressions represent the same function, these two coefficients must be equal. Negative 1/6 equals negative 1 over pi squared times the sum of 1 over n squared. Multiply both sides by negative pi squared. The negatives cancel. Pi squared over 6 equals the sum of 1 over n squared. And there it is. The Basel problem is solved. The sum of the reciprocals of the perfect squares is exactly pi squared over 6. One of the most surprising equations in all of mathematics. You can see this convergence on a graph. Plot the partial sums as a sequence of points. The first point sits at 1, the second at 1.25. Each successive point is a little higher than the last, but the jumps get smaller and smaller. The points approach a horizontal line from below. That line sits at pi squared over 6, approximately 1.645. The partial sums never reach the line, but they get as close as you want. After a million terms, the sum agrees with pi squared over 6 to the 5th decimal place. Now, was Euler justified in treating sine of x over x as an infinite polynomial? At the time, he had no rigorous foundation for doing so. He was making an analogy. Polynomials factor by their roots. Sine of x over x has roots, so maybe it factors the same way. This is the kind of reasoning that can lead you astray. But in this case, Euler was right. About a century later, Carl Weierstrass proved the factorization theorem for entire functions, which states that any entire function can indeed be expressed as a product over its zeros up to an exponential factor. For sine of x over x, the exponential factor turns out to be 1. Euler's intuition was vindicated 100 years after he trusted it. The Basel problem is not an isolated curiosity. The sum of 1 over n squared is the value of the Riemann zeta function at s equals 2. Euler did not stop at zeta of 2. He computed zeta of 4, which is pi to the 4th over 90. He computed zeta of 6, pi to the 6th over 945. Every even positive integer gives a rational multiple of the corresponding power of pi. But the odd values are a different story entirely. Zeta of 3, the sum of 1 over n cubed, was proved irrational by Roger Apry in 1978, but no one has found a closed form for it. Zeta of 5, zeta of 7, and all higher odd values remain wide open. We do not know if they involve pi. We do not know what they involve. A sum of fractions. The simplest possible ingredients. 1 over 1, 1 over 4, 1 over 9, 1 over 16, 1 over 25. You add them all up, forever, and the answer is pi squared over 6. Not because of any geometric argument, not because circles are secretly involved, but because the sine function has zeros at every integer multiple of pi, and those zeros constrain the Taylor coefficients of sine of x over x. The structure of the sine function forces the sum of 1 over n squared to equal exactly pi squared over 6. The answer was always there, encoded in the zeros of sine. Euler was the first to see it.